NENOMATICA, where mathematics meets YouTube excellence. Exponential inequalities. Welcome to our video on exponential inequalities. Today we'll learn how to solve inequalities involving exponential expressions, like the one shown on your screen. Let's look at our example. We need to solve the inequality a to the power of f of x is greater than a to the power of g of x. To solve this type of inequality, we need to understand that the solution depends on whether the base of the exponential function is greater than 1 or between 0 and 1. The base value affects whether the function is increasing or decreasing. Let's examine our first case where it is greater than 1. In this case, the exponential function a to the power of x is an increasing function. This means that if the exponent increases, the value of the function also increases. So when it is greater than 1, for the inequality a to the power of f of x is greater than a to the power of g of x to be true, we need f of x to be greater than g of x. Now, let's look at our second case, where it is between 0 and 1. In this case, the exponential function a to the power of x is a decreasing function. This means that if the exponent increases, the value of the function decreases. So when it is between 0 and 1, for the inequality a to the power of f of x is greater than a to the power of g of x to be true, we need f of x to be less than g of x, which is the opposite of our first case. Let's summarize what we've learned about solving exponential inequalities. When solving an inequality of the form a to the power of f of x is greater than a to the power of g of x, if it is greater than 1, then we need f of x to be greater than g of x. If it is between 0 and 1, then we need f of x to be less than g of x. Let's look at our example. We need to solve the inequality 25 to the power of x is greater than 125 to the power of 3x minus 2. When solving exponential inequalities, we first need to get both sides to the same base. Let's rewrite our problem using base 5. Since 25 equals 5 squared and 125 equals 5 cubed, we can write our inequality as 5 squared to the power of x is greater than 5 cubed to the power of 3x minus 2. Now, we need to simplify the expression using the power of a power rule. This rule states that when we have a power raised to another power, we multiply the exponents. So for the left side, 5 squared to the power of x becomes 5 to the power of 2x. Similarly, for the right side, 5 cubed to the power of 3x minus 2 becomes 5 to the power of 3 times the quantity 3x minus 2, which simplifies to 5 to the power of 9x minus 6. Now we have the same base, 5, on both sides. For exponential inequalities with a base greater than 1, like we have here with base 5, we can compare the exponents directly while maintaining the same inequality sign. So our inequality becomes 2x is greater than 9x minus 6. Now we can solve this like a regular linear inequality. Let's subtract 9x from both sides of the inequality. Simplifying, we get negative 7x is greater than negative 6. Now we need to divide both sides by negative 7. Remember, when we divide both sides of an inequality by a negative number, we must reverse the direction of the inequality sign. So dividing by negative 7, we get x is less than 6/7. Therefore, the solution set in interval notation is all real numbers from negative infinity to 6/7, not including 6/7 itself. This is written as the open interval from negative infinity to 6/7. Let's begin with our example. We need to solve the inequality where 1/10 raised to the power of 4x squared minus 2x minus 2 is less than or equal to 1/10 raised to the power of 2x minus 3. First, let's recall important properties of exponential inequalities. For exponential expressions with the same base, we need to consider whether the base is between 0 and 1. In this case, our base is 1/10, which is between 0 and 1. Because our base is between 0 and 1, we need to reverse the inequality sign when we remove the exponents. So 4x squared minus 2x minus 2 is greater than or equal to 2x minus 3. Now, let's rearrange the inequality to standard form. We'll move all terms to the left side to get 4x squared minus 2x minus 2 greater than or equal to 2x minus 3. Then we combine like terms. 4x squared minus 4x plus 1 greater than or equal to 0. Let's factor this expression. We can rewrite 4x squared minus 4x plus 1 as 2x minus 1 squared greater than or equal to 0. Now, we need to find when this inequality is satisfied. We know that the square of any real number is always greater than or equal to 0, so the expression 2x minus 1 squared is always greater than or equal to 0 for any value of x. This means our solution set is all real numbers. We'll solve this example where we need to find values of x that satisfy the inequality. 1/3 raised to the negative absolute value of x minus 2 is greater than or equal to 81. Let's start solving this problem step by step. First, we'll rewrite 1/3 as 3 to the power of negative 1, which gives us 3 to the negative 1, all raised to the negative absolute value of x minus 2 is greater than or equal to 81. Next, we'll apply the power rule for exponents, which states that when a power is raised to another power, we multiply the exponents. Since we have a negative power of a negative power, the negatives cancel out, giving us 3 raised to the absolute value of x minus 2 is greater than or equal to 81. We also note that 3 is greater than 1, which will be important for determining the direction of the inequality. Since we know that 3 is greater than 1, the inequality maintains its direction when we take logarithms of both sides. Applying the property of logarithms, we can bring down the exponents, giving us the absolute value of x minus 2 is greater than or equal to 4. Now, we need to solve the absolute value inequality. Remember, the absolute value of an expression is greater than or equal to a positive number when the expression inside is either greater than or equal to that positive number, or less than or equal to the negative of that number. So we have two cases. Case 1, x minus 2 is greater than or equal to 4, which gives us x is greater than or equal to 6. Case 2, x minus 2 is less than or equal to negative 4, which gives us x is less than or equal to negative 2. Therefore, our solution is the union of two intervals x is less than or equal to negative 2, or x is greater than or equal to 6. Using interval notation, the solution set is d equals the interval from negative infinity to negative 2, closed at negative 2, union with the interval from 6 to positive infinity, closed at 6. To summarize, closed at negative 2, union with the interval from 6 to positive infinity, closed at 6. To summarize what we've done, first, we rewrote 1/3 as 3 to the power of negative 1. In this video, we'll solve an exponential inequality using algebraic techniques. Let's start with the given inequality. Let's begin by converting the base 0.04 to a fraction. We can write 0.04 as 4 divided by 100. Next, we can simplify this fraction to 1 over 25. Now, we can express 1 over 25 as 5 to the power of negative 2. This is because 5 squared equals 25, and 1 over 25 is 5 to the negative 2. Using the power rule for exponents, which states that the power of a power is the product of the powers, we can multiply negative 2 by the expression 5x minus x squared minus 8. Distributing negative 2, we get 5 to the power of negative 10x plus 2x squared plus 16. And on the right side, we can express 625 as 5 to the power of 4, since 5 to the 4th equals 625. Since 5 is greater than 1, the inequality sign remains the same. Since both sides now have the same base, 5, and 5 is greater than 1, we can directly compare the exponents. This gives us the inequality 2x squared minus 10x plus 16 is less than 4. We can divide the entire inequality by 2 to simplify it further. This gives us x squared minus 5x plus 6 is less than 0. To solve this quadratic inequality, we need to find the zeros of the polynomial x squared minus 5x plus 6. We can factor this as the product of x minus 2 and x minus 3. Setting each factor equal to 0 gives us x equals 2 or x equals 3. Since the coefficient of x squared is positive, the parabola opens upward. This means the expression x squared minus 5x plus 6 is negative between its two zeros. Therefore, the solution to our inequality is x is between 2 and 3, or in interval notation, x is in the open interval from 2 to 3. Let's look at this example. We need to solve the exponential inequality x raised to the power of log x is greater than 10. Since we're dealing with an exponential inequality, our first step is to take the logarithm of both sides. This gives us log of x raised to the power of log x is greater than log of 10. Now, we apply the logarithm property that says log of a raised to the power b equals b times log of a. So log of x to the power log of x becomes log x times log x. We can rewrite log x times log x as log x squared. When we have a squared term greater than a positive number, we need to take the square root of both sides. This gives us the absolute value of log x is greater than 1. Now, we need to split this into two cases because of the absolute value. Case 1, log x is greater than 1, which means x is greater than 10. Case 2, log x is less than -1, which means x is between 0 and 1/10. Therefore, the solution set is the union of two intervals, from 0 to 1/10, union with the interval from 10 to positive infinity. So our final answer is this domain D. Let's look at the following example. When we need to solve an inequality that contains expressions like this, we need to analyze each part carefully. First, let's note that we have a square root term. For any square root to be defined, the expression inside must be non-negative. So we need 6 minus x to be greater than or equal to 0, which means x must be less than or equal to 6. Now, we need to analyze when this product is greater than or equal to 0. A product is non-negative when either both factors are non-negative or both are non-positive. Since the square root is always non-negative when defined, the expression will be greater than or equal to 0 precisely when the second factor is also greater than or equal to 0, given our domain restriction x less than or equal to 6. Let's focus on the second factor. We have 5 raised to a quadratic expression minus 25 times the square root of 5. We can simplify 25 times the square root of 5 as 5 squared times 5 to the power of 1/2, which equals 5 to the power of 2.5. Now, we can rearrange the inequality to 5 to the power of x squared minus 7.2x plus 3.9 is greater than or equal to 5 to the power of 2.5. Since the base 5 is greater than 1, an important property of exponential functions tells us that the inequality for the exponents maintains the same direction. This means we can extract the exponents and say x squared minus 7.2x plus 3.9 is greater than or equal to 2.5. Subtracting 2.5 from both sides, we get the quadratic inequality x squared minus 7.2x plus 1.4 is greater than or equal to 0, keeping in mind our domain restriction that x is less than or equal to 6. Now, let's solve this quadratic inequality. The discriminant is b squared minus 4ac, which gives us 7.2 squared minus 4 times 1 times 1.4. This equals 51.84 minus 5.6, which is approximately 46.24. Since the discriminant is positive, the quadratic has two real roots. Using the quadratic formula, the roots are approximately 0.2 and 7.0. Since the coefficient of x squared is positive, the quadratic function opens upward. So the inequality is satisfied when x is less than or equal to 1/5 or when x is greater than or equal to 7. Finally, we need to combine this solution with our domain restriction, x less than or equal to 6. The intersection of our solution set with the domain restriction is x in the interval negative infinity to 1/5, closed, union with the singleton set containing 6. Thus, the solution to our original exponential inequality is the set of all real numbers less than or equal to 1/5, along with the specific value of 6. Here's our example problem. We need to solve the following exponential inequality. Let's begin solving this inequality. First, we'll move all terms to one side to compare with 1. We start by multiplying both sides of the inequality by 5 and dividing both sides by the right side expression. The right side simplifies to 1. Let's rewrite our inequality. Now, let's simplify the denominator. We have 5 times 25 over 7, which equals 5 times 25 divided by 7. 25 is 5 squared, so altogether we get 5 cubed divided by 7. Let's rewrite this more clearly. In the denominator, we have 5 times 5 squared over 7 times 7 to the 2x times 5 to the 3x. Simplifying, we get 5 cubed over 7 times 7 to the 2x times 5 to the 3x. Now, we can reorganize our fraction. We'll split up the terms in the numerator and denominator to simplify using laws of exponents. Using the laws of exponents, we combine the powers. For the base 5, we get 5 to the negative 3 plus 2x minus 3x, which is 5 to the negative 3 plus negative x, or 5 to the negative x minus 3. For the base 7, we get 7 to the 3x plus 2 minus 2x plus 1, which is 7 to the x plus 3. We can rewrite this as 7 to the x plus 3 divided by 5 to the x plus 3. This is equivalent to the fraction 7 over 5, raised to the power of x plus 3, being less than or equal to 1. Now, we need to determine when this inequality is true. Note that 7 divided by 5 is greater than 1. When a fraction greater than 1 is raised to a power, it will be greater than 1 if the power is positive, and less than or equal to 1 if the power is 0 or negative. Since 7 over 5 is greater than 1, for our inequality to be satisfied, the exponent x plus 3 must be less than or equal to 0. Solving for x, we get x is less than or equal to negative 3. Therefore, the solution set is the interval from negative infinity to negative 3. Welcome to our lesson on solving exponential inequalities. Let's begin with an example problem. When solving exponential inequalities, we first need to understand the properties of our exponent. Let's analyze the expression in the exponent, 2 plus 4 plus 6 plus dots plus 2x. We can notice that this is an arithmetic sequence with first term 1, common difference 1, but each term is multiplied by 2. So this equals 2 multiplied by the sum 1 plus 2 plus 3 plus dots plus x. Now, we can use the formula for the sum of the first n natural numbers. The sum of the first x natural numbers equals x times x plus 1 divided by 2. Substituting this formula, we get 2 times the quantity x times x plus 1 divided by 2, which simplifies to x times x plus 1. So our original inequality can be rewritten as 3/10 raised to the power of x times x plus 1 is greater than 3/10 raised to the power of 72. We also note that 3/10 is between 0 and 1, which is important for determining the direction of our inequality. When we have a base between 0 and 1, and we're comparing powers of this base, the inequality sign flips. This happens because as the exponent increases, the value of the expression decreases. So our inequality means that x times x plus 1 must be less than 72. We expand x times x plus 1 to get x squared plus x. So we have x squared plus x is less than 72. Let's rearrange this into standard form. To solve this quadratic inequality, we need to find values of x where x squared plus x minus 72 is less than 0. Let's find the roots of the quadratic expression by factoring or using the quadratic formula. After solving, we find that the roots are x equals negative 9 and x equals 8. Using the sign analysis, the function is negative between these two values, so our solution is negative 9 is less than x, which is less than 8. However, since the problem specifies that x must be a natural number, we need to further restrict our solution to the natural numbers in this interval. Since we need natural numbers and the interval negative 9 to 8 includes the natural numbers 1 through 7, our final solution is the domain D is the set of natural numbers from 1 to 7, which we can write as 1, 2, 3, 4, 5, 6, 7. And that's how we solve this exponential inequality. To recap, we 1. Simplified the exponent expression. 2. Applied properties of inequalities with bases between 0 and 1, 3. Converted to a quadratic inequality. 4. Found the interval solution. 5. Restricted to natural numbers. The answer is the set of natural numbers from 1 to 7. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.